This question is from GATE 2022 Mechanical Engineering paper set 1, question number 64. Consider a solid slab whose thermal conductivity K is 10 watt per meter per Kelvin with thickness 0.2 meter and of infinite extent in the other two directions as shown in the figure. Surface 2 at 300 Kelvin is exposed to a fluid flow at a free stream temperature T infinity of 293 Kelvin with a convective heat transfer coefficient H of 100. Surface 2 is opaque, diffuse and grey with an emissivity epsilon of 0.5 and exchanges heat by radiation with very large surroundings at 0 Kelvin. Radiative heat transfer inside the solid slab is neglected. The Stefan-Boltzmann constant is 5.67 into 10 to the power minus 8 watt per meter square per Kelvin raised to 4. The temperature T1 of surface 1 of the slab under steady state conditions is dash Kelvin. Round it off to the nearest integer. Let's solve this one. Now, according to the energy balance, we can say that the heat that is transferring by conduction through this slab, if we take it as Q conducted heat transfer in conduction, will be equal to the convective and radiative heat transfer taking place between the surface 2 and this outside environment. So Q convective and Q radiative. This escaping heat should be equal to sum of these two amounts of heat. So we can write Q by conduction, conductive heat transfer, will be equal to convective heat transfer plus the radiative heat transfer. Now each of these heat transfer values we can substitute. So heat through conduction is given by Fourier law, which is K thermal conductivity into area. We have to take unit square area. So we can take A as 1 and dt by dx will be equal to convective heat transfer will be H, the heat transfer coefficient, into T2, which is the surface temperature, minus T infinity, which is the temperature of this surrounding medium, plus Stefan-Boltzmann constant sigma into emissivity epsilon into again T2 raised to 4, which is the temperature of the surface 2, minus TE raised to 4. Because they have mentioned that the radiative heat transfer takes place with very large surroundings from the surface 2 at 0 Kelvin. So this temperature TE is 0 Kelvin, which is given. Let's substitute all the values here. So K is given to be 10 watt per meter Kelvin into this dt is nothing but difference between surface 1 and surface 2's temperature. So we can write it as T1 minus T2, and T2 is given to be 300 Kelvin. So we'll directly substitute it here, 300 Kelvin divided by dx is the thickness of the slab, which is 0.2. This will be equal to the heat transfer coefficient H is given 100 watt per meter square Kelvin. We need not convert any of the units. All units are mentioned in the SI system. So into T2 is again 300 Kelvin minus T infinity is mentioned here, which is 293 Kelvin, plus Stefan-Boltzmann constant is given 5.67 into 10 to the power minus 8 watt per meter square per Kelvin raised to 4. Emissivity is given as 0.5 into this temperature T2 is again 300 Kelvin raised to 4 minus TE I already explained, it is 0 Kelvin. So 0 raised to 4. Now rearranging this in order to find out T1, because that's the question that we have to find temperature of surface 1. T1 will be equal to, this first term is 700. We'll keep the right hand side terms in the bracket so that we can multiply the right hand side to 0.2 by 10. So in the bracket this first term is 700 plus this second term turns out to be 229.635. This minus 300 on the right hand side becomes plus 300. This gives us the answer T1 as 318.593 Kelvin. But we need to write the answer in integer form, so we can write it as 319 Kelvin as it is the closest value to 318.593. Let's go back and fill in this answer. The temperature T1 of surface 1 of the slab under steady state conditions is 319 Kelvin. To learn more about Fourier's law of heat conduction and to learn about other heat transfer forms, you can refer to the NPTEL video Fourier's law of heat conduction. This and other videos from the course Continuum Mechanics and Transport Phenomena. This is taught by Professor T. Ranganathan. He is from IIT Madras. I hope this solution helps you clear your doubt. Thank you.